So welcome to the second half of this 10th class. Now we'll go in a form of unsupervised learning, essentially, right? Although people don't use the word unsupervised learning for graphs that often. I just told one of your friends during the break that if you hear the word graph and learning together, usually it means supervised learning. Just a context of the way the word's used. But anyway, the reason I consider centrality analysis a form of unsupervised learning because, well, again, there's no label, there's no right or wrong. How you characterize the data depends on your perspective, your organizing schema, okay? Just like in cluster analysis, right? You get one clustering if you define closeness as physical distance, geographical distance. For example, how close you are on a latitude and longitude, right? On the other hand, you can say, well, if you have two communities across the river, right? The two houses across the river may actually belong to two different communities, even though physically they are close by latitude and longitude. So it's kind of like contiguous mass, contiguous or density kind of sense of a community. In that case, clustering would get something else. Same here, right? I mentioned a few ways of thinking about centrality of a network. Okay, so think of if I'm not if a particular vertex is not here, the whole network tend to fall apart or kind of like divides up, right? Gets unconnected. In that case, clearly number 12 is definitely very central to this network. Okay, but if I'm talking about, say, efficiency of communication, like the shortest distance to all the members, okay, so that I can pass gossip or message with the quickest or the fastest spread of information, fastest spread of infection or information, right? Maybe 24 is better, right? Maybe 24 is better. Now, so here and this kind of analysis is kind of algorithmic. You can't just sort of like eyeball it. In this case, you can perhaps, but in a big data, in a large data size, you need an algorithm, and that's where centrality algorithm comes in. Okay. To be honest, I mean, this is kind of like a private note. I'm very, one of the things that's kind of like highlight of my career is that I could almost claim that I was the first guy, one of the first, if not the first person in Thailand to actually bring network centrality to the analysis of data. I did this long before social network analysis was a thing. The reason I did this was because I was in the Bank of Thailand, and we were looking at crisis preparedness, the banking system. How frail is a banking system? Okay. Now, Bank of Thailand doesn't care if an individual bank fail. Bank of Thailand cares if a system fail, right? Because it affects the whole banking network. So there's some kind of like a natural banking network. So think of it this way. If this were like, instead of network of some number that I randomly generate, let's say this is some kind of connectivity between financial health. Okay. So this could be banks, right? So if this bank, traditionally, too big to fail means what? Look at the size of the bank. Okay. Look at the size of the bank. So maybe this bank is really big. So the focus should be on this bank. Number 12 is a small bank. So you shouldn't really care about bank number 12, okay? But in terms of network, maybe the 12 bank, you can think of bank, you can think of company, you can think of supply chain. Maybe a less dramatic case would be like supply chain breakdown, okay? So yeah, maybe we can talk about that. So supply chain, we say this one here may be a small link in the logistics. Okay, logistics is another good word and another good example. Maybe this is not a big road. It's not a big warehouse, but it's the warehouse that actually store everything from here and send it to over here. And if you don't have this thing, you can't send it. Okay, so maybe this is kind of like offshore loading a barge or something like that. Okay, so there's a lot of this application, and like this is show you example. This was actually my work way back in. Oh no, what's it? 51, 53? Yeah, literally 20 years. 46, 46. Yeah, 17 years ago, I think, something like that. Okay, so you can say that, hey, I want to look at how different banks are important. And here's a funny thing is, I was trying to introduce this concept to say the Bank of Thailand, right? That banks are important not because they are big. Okay, you should look at this bank not because it's big, but because it has interconnectedness with other banking. Now, why are banks interconnected? Because you put money at a bank, right? That's your saving account. But banks have a lot of money at the end of the day. Okay, some have more liquidity than they need, some have less, so they actually lend to each other. This is called interbank lending. Okay, so even though you are familiar with borrowing from banks, but on a daily basis, banks borrow from each other, and that's how they draw liquidity from each other. At a given moment in time, a big bank can have a lot of people take money out of their ATM, so they actually are short, so they need liquidity from other banks. So this is called liquidity channel. Okay, the point is that with the Thai banks, how do you know which one has a network importance? Which one is a central bank in terms of a network? Okay, commercial bank, okay, not central bank like the Bank of Thailand, but central in the sense of centrality. So I did this kind of proposal, but the example that I did, just to make the concept concrete, instead of saying that there's a network of bank, I say it's a network of Premier League football, right? When you want to see which football team is good, you can look at the win record at the end, right? So who's the best team? Who's the best team at the end of the season? It's the one that won the premiership, right? Okay. Now that could be the case. Now, but imagine you could win the premiership because for some reason you are a strong team. Imagine that you have you can rank out how strong teams are from 1 to 20. And based on the schedule of meeting, okay, the strong team ends up meeting all the weak teams. So it keeps getting 3 points for wins, throughout the season. So obviously at the end of the season, this guy is going to have the highest championship point, right? But that championship point comes from beating weaker teams. So in order to actually say who is really actually the strongest team, you should say you are strongest team because you beat a lot of teams that are strong. And how do you know that the other teams are strong? Because they themselves are beating other teams that are strong. And those other teams are strong because they beat other teams that are strong. So this is kind of a recursive equation. Okay. So if you solve this recursive equation, by the way, do you guys remember from linear algebra? Eigensystem? Eigensystem? Yeah, this is actually that. If I have a matrix of all the football team, okay, 20 team, and I have ij, I beats j is equal to 1, okay, right? If I wins over j is equal to 1, so maybe if they play more than once, it's a weighted matrix, so maybe 3, because this team, when they meet, I beat j 3 times, but ji is 1 because j only beats I 1 time, something like that. Okay, now that matrix is an adjacent matrix. If you did what's called eigenvalue decomposition, and you get what's called principal component, which again was in part of the dimensionality reduction, you look at the value. The one with the highest number are the strongest team. Okay, now you don't have to know this. This is kind of highly technical, but it's kind of like a nice story. You know, a football team has nothing to do with banking system, right? But the principle in which I say which team in a English Premier League is the strongest team at the end of the season may not be the one that won the Champions League. Okay, and if the scheduling comes slightly differently, this team is actually the strongest team. So if you want to take at the end of Premier League, right, and maybe place a bet on UEFA, okay, you should look at who won the British Premier League. Maybe you should look at the one that has the highest eigenvector centrality score. Okay, I use that to show which bank in Thailand has the most network leverage. Okay, so I use the word network leverage, but basically the concept is centrality. So I did this back in 2006, maybe. Yeah, I think 2006, 2007. Anyway, so it's quite a very important area that I found very useful. And then of course, 4 or 5 years later, when social network became, took off, you use this kind of thing. So now I can take a network of friends and also say who is really popular. Just like a strong British football team is a strong team because this team wins against strong teams. And what are those strong teams? They're a strong team because they win against strong team. Okay. Likewise, a bank has high network leverage because it's highly interconnected with banks that are themselves exerting high network leverage because they themselves are linked to banks with high network leverage. Somebody who's popular on a Facebook page is popular because he or she is linked to a lot of popular people. And those people are popular because they are linked to a lot of popular people, right? Now, this is called eigenvector centrality. Now, let me tell you another story. And this is, for those of you who want to say, when does mathematics pay? When I was doing a PhD, internet search engine was coming out. For my own PhD thesis, I think I rely on what's called Alta Vista as a search engine. And then Google came along. Google did not win yet. It was a small player. I think by the time I got my PhD, or maybe a year or two afterward, Google beats everybody. Now you use Google. You don't use Alta Vista. You don't use Netscape. You don't use Gopher. You don't use anything. You use Google. Do you know why? Because the Google search engine prioritize results based on eigenvector centrality. Now they add their own secret sauce, well, not secret sauce, special sauce, and they call it page rank algorithm. Page rank algorithm is an embellished or advanced or improvement on eigenvector centrality concept. Okay, and they use that so that when you do a search, people end up on a strong page. Why are those pages strong? Because they are linked to by strong page. And why are those pages strong? Because they themselves in turn are linked to by a lot of strong pages. Okay, so if you link to by a lot of silly little pages, conspiracy theory pages or something like that, maybe that, you get a lot of 5,000 pages linked to you, but you're not that important. But if you get 500 pages linked to you, but each of those 500 pages get linked to by millions or whatever, right? You get this accumulative avalanche of information, okay? So that's how Google beats everybody, okay? And that algorithm called PageRank algorithm is here. So this three thing here, you can double click. Eigenvector centrality, I recommend you read it first because that's the concept. That's the one I use for the Bank of Thailand, okay? And cat centrality is kind of like embellished on this, I guess you can say that. So all these are kind of based on similar concept, Okay, so there's some weakness, there's some pro and con of using one or the other. So cats help something. So page rank, maybe you can say the page rank is an improvement on cat, which is an improvement on eigenvector centrality, but it's based on the same kind of concept. You are important, not because you know a lot of people, because you know a lot of people, important people. How do you know the people you know are important? Because they themselves know a lot of people who are important people. And it's a recursive equation. Okay. So again, this is not a machine learning class, so I won't go deep into how it's done, just so you know that these are done. Now, there's another kind of centrality, which is, I think, simpler to understand. This one simply called degree centrality. The number of edges connected to you is actually degrees. So you are ranked based on how many direct connections you have. So this is kind of like counting links. Okay, so this is again not as good. So you can imagine that, you know, right around the time I graduated, I got my PhD, or maybe after, the internet search engine were using different way to rank the search result. Maybe some company use degree centrality. That turned out to be not so very robust. It's not very good. Okay, so because Aaron and Paige, the co-founder of Google, use eigenvector concept, but you know, they modify it further, call it PageRank centrality, and they get that result. So this is simple concept, degree centrality. I don't really recommend using that very much. Eigenvector, cats, and PageRank, these are the one that I would use. Professionally, I have. Okay. Finally, there's this thing called betweenness centrality. Now, this one is entirely different from these guys. The idea is you have an algorithm. It's a little bit like efficiency of that message passing. If I say, okay, here's a network. Here's a network. Okay, here's a network, and let's say you hold each other's line message, right? Now, from this guy all the way here to that guy all the way here, okay? What is the shortest path? Shortest path means minimum number of links, okay? Shortest number of path. I calculate shortest path, right? For every pair, okay? If there are n of you, how many pairs are there? It's n times n minus 1 divided by 2, okay? Basically, it's the number of entries on the lower triangle of the matrix. It's n times n plus 1 divided by 2. Okay, so if there are 40 of you, how many connectivity, undirected connectivity can you define? It is 40 times 39 divided by 2. Okay, now for each of those for each of those, I calculate the shortest path. Then for every one of you, okay, I ask, how many times did the shortest path go by you? So look at this page. Look at this example. Okay. So let's say the shortest path from 2 to 16, it passed to 12. Okay, it passed to 1. Right? So from 2 to 18, okay, the path passed to this guy, passed to this guy. From any of these guys to the rest, maybe pass to this. But from 14 to 16, do I need to pass to 1? Do I? I don't. Okay, never mind shortest. I don't even need to pass through it, right? So 1 is definitely not going to be one of those. Maybe 12 is a good number. Okay, but you don't know this because the complexity of the shortest path is not something you can eyeball. Okay, but basically all these nodes, I take all the shortest path, I list them, and then ask, how many times did the shortest path involve you? Number 10 say 1, because it's only one shortest path from himself to everybody, right? Sorry, not 1, but n minus 1, right? From him to 9, from him to 7, from him to 8, from him to everybody. So that's n minus 1. So n minus 1 shortest path passed through him. Okay, but that's very tiny compared to n times n minus 1. That's basically n squared. Okay, so let's say you have 20 here. This guy would have 19 paths that pass through him. Okay, but this one may have 300. Okay, let's rank them based on number of shortest paths requiring you. Why? How would you think of this? Think of traveling. Yeah? Think of this as Jangwat or province in Thailand. And think of this as highway. Right? Think of highway. If you want to go from this province in the south to this province in the northeast, okay, you probably have to pass through Bangkok or something, right? If from the north to the north, you don't need to pass through Bangkok, but from the south to the north, yeah, okay, and something like this. So for every transportation network, this concept is even more important than page rank or eigencentrality, eigenvector. Okay, so it depends on which thing. So if you're going to analyze, like, think of this as maybe supply chain hub, right? Something like that. So shortest path, very important in logistics. How do I do it? Very easy. Now, this one, I want you to go through. It's a little bit hard to, because I wrapped this already. Now, these are names of method. Okay, these are names of method. Degree centrality, you already saw that. Eigenvector, page rank, betweenness. Oh, there's cat centrality as well, but yeah, never mind. So I should put cat centrality. So this, 3, 4, those are the one I use. This kind of like a function that I use to wrap this analysis. Okay. Basically, it creates interactive plots. So by the time we get to this part of the book, kind of assume that you know how to do interactive. So instead of just showing the function, I show you the whole manipulate thing. But here's an example. Right? So let's say, okay, let me just highlight this and shift enter the whole thing just to make sure it runs quickly. Why is it not running? Yeah, your laptop again. Okay, I think your laptop doesn't like it when I do multiple cell at once. So I have to do it one by one. I don't know why that is, by the way. Adjacency matrix. I don't know why that is, but okay. Oops. Well, let's take one example. Let's take this guy, connectivity les mis, okay? This guy. And you could I'm just gonna do then eigenvector centrality. Okay, so now this looks a little bit matrix form. Okay, now let's multiply by 100 just so that actually normalize. Okay, normalize is a way of scaling, so it adds up to 1 or whatever. So you can see that on average, well, that doesn't look very nice. So let's make it 100 times. Okay, let's make it round. Okay, so this is kind of like a more like actually, okay, just some index. The whole point is that these are 77 class number, okay, class member, and you can literally see that these guys, remember the fifth, sixth, seven, I don't know who that is. It doesn't matter, doesn't bother me. It's not very important. So this guy probably are like minor character, okay? Maybe people walking the street or something. But this guy certainly has a relatively high centrality number. So you can say who is the most important. Now, important here doesn't mean a lead character or not, but important here means, appears a lot of character. Now, here's a fun thing. Here's a fun thing that I did. Okay. So this is in the notebook. This is in the notebook. Okay, it's in the notebook. But I want to show you. Okay. We might not be able to finish today, but I want to show you another example. Okay. So this is something that you can play with. And again, I would get different result if I don't use eigenvector centrality. If I use something like a betweenness, okay, I get different number. Oh, this thing is more, so this guy doesn't belong to the shortest path at all, right? Remember that? So this guy like doesn't really matter. So these are once again, these are kind of characterization. Okay. So think of it this way. I come to this room, okay? I say, okay, guys, go line up in front of the class from the tallest to the shortest. So I take original data and I go to a rank. The reason this thing is called page rank is because by looking at connectivity, I compute some number called page rank. And based on that number, I can see who has highest page rank centrality. Okay? Does that make sense to you? Okay? So there's some intricacy. We'll flesh this out in the project. So if your project involves graph data, then you work with, say, me or your TA. Why do we use betweenness centrality? Why do we use cap centrality? This centrality is good for symmetric matrix, but it's not good for, acyclic matrix. So these are kind of like a professional have to know which tool is right for the job. Okay, you just have to know that there are tools for the job. Okay, your level is to understand that there are tools for the jobs. Which tool is right for the job depends on whether or not you're going to do this for your project. If you're going to do this for your project, you're going to have to dig deeper. Okay, so based on some data set, so let's say chances are if you're working with logistic or supply chain, okay, or some kind of warehousing configuration, maybe if you want to do this, you will have to involve yourself with betweenness centrality. Okay, degree centrality maybe doesn't make any sense. Okay, in fact, degree centrality usually is not. I never ever use that rarely ever in practice. Okay, but your mileage may vary. Okay, so that's how this works. Now, I want to briefly, okay, go to you have internet. What do you use? Okay. And tight. It takes a while. I might as well look. Does it come up? Where's the internet? Okay. Okay, go to YouTube. Actually, you can type along. You might get there faster even. Okay. And good thing with having a, okay, just type in my name. You go, okay. Now, let me see. Go to playlist. This is the previous class. So your class is here. Python. Right. Graph theoretic computation. I'm not going to play this because it's going to take a while. You can watch it on your own. Okay, so this is social network analysis. Now, because this is a PyCon Thailand, obviously I didn't use Mathematica. I use Python to demonstrate the concept. But here's the deal. Let me just quickly like run through the slides. Actually, I think I have the slide with me. Hold on. Might be easier. Might be easier. Give me a minute, okay? Let me just say PyCon. Okay, PyCon. There is PyCon fuzzy graph theoretic formatting. Okay, there you go. Basically, it's that slide, except back then I was working for SCD, so I could use the logo, but no. So basically, this is what I want to, yeah. Okay, right. Actually, I can give this to you as well, but I'll talk through first. Okay, so this is the picture that I didn't have at the beginning of the class. This is actually Königsberg. Okay, this is Königsberg. Okay, this is a landmass, this is a landmass, this is a landmass, right? You can see that this landmass and this landmass is connected by two bridges, right? So in this case, it's not like knowing because you have more than one, right? So you can have 0, 1, 2. So what kind of number would this be? This would be kind of ordinal, right? Right? And it's also symmetric because why? Because it's not a one-way. Back then they didn't build one-way bridge. If you can go from A to B, you can go from B to A. So instead of saying, hey, let's try if you can walk all this in one tour. Let's say this is a dot. Let's call this thing, okay? This thing becomes this point, which is a vertex. This thing is a vertex. This thing is a vertex. This thing is a vertex. There are actually 1, 2, 3, 4 vertices. How many edges? 1, 2, 3, 4, 5, 6, 7. Hence, 7 bridges of Königsberg. Okay? Now, this is what the graph looked like. I don't know if you can see. This is basically the graph representation. So I have 1, 2, 3, 4. 1, 2, 3, 4. I have on the diagonal, do I have any number? No, because you don't have a bridge from the land to itself, right? So on the diagonal, nothing, right? And then you have 1. Now, how many numbers do you have? You have 7 ones on the lower triangle. But if you go to the top triangle, you get another 7, exactly the same, right? So if I take this a matrix and I count the edge, it will be 7. Okay. So that's what this graph is. So that's the origin of this thing. Okay. Now this is reference back to my work with the Bank of Thailand. We don't have to go very far. But here's the thing. Okay, let me go. Let me skip this and I'll come back. Let me go to here. This is a little bit like British football league. Okay, except instead of having 20 football league team, I think at that time people were playing Overwatch. Do you guys play games? I don't, by the way. I don't. Apparently, there's a matrix of character strength. Okay, there's a matrix of character strength. So, for example, you can say that, I don't know, Zendaya. Okay, Zendaya beats Tinker or Tracer. I don't play. Okay, this is what happened when the character from Overwatch, when they meet each other, who beats whom. Okay, I think blue means row beats column. Red means column beats row or something. I'm not quite sure. Okay, obviously this is asymmetric. Okay, asymmetric because it's not a round robin. So maybe some of them never met each other, or maybe they have equal strength. Okay, so basically, apparently, according to this PC Gamer Overwatch Hero Counters guides, this is who's important. Okay, now you want to pick a player. Okay, if you are naive, you may just look at individual and say how many characters do you win. Okay, so count number of blue or something, but that's not smart. What's smart is to make this into a matrix, runs an eigenvector centrality analysis on this, and don't quote me, okay? Don't quote me, but I think from the analysis, Zendaya is the strongest player, if I'm not mistaken. I don't know why the name stuck. Maybe because it's the last name, or yeah. Okay, so this is the data. Okay, so Genji and McCree and Pharaoh and all that stuff. So this is what relative strength of Overwatch. So I solved that. Okay, so this is like a football league. Okay, so based on this data, so now this obviously is weighted, right? Because it's not 0 and 1. Okay, 1 means just kind of even, I think. Okay, so solve that. Now this is what I did for the Bank of Thailand. Now this is a different story. Okay, now here's a fun one. I'm going to skip this because there's a graph computation before you get to this. Okay, right. This is a kind of graph I haven't mentioned. Okay, I haven't mentioned. It's called Erdos. This is good. This is good. There's actually a website where you can say which two actresses or actors are connected. So, for example, Tom Hanks and Tim Allen has direct connection because they appear together in the same movie. Okay, so remember that the Les Miserables, right, appear together on the same stage. This is like the same thing except Hollywood actor and a movie. Okay, now if this guy and this guy appear to the same movie, okay, it's called connection 1. Okay, connection 1. If this guy and this guy act together and say, what's it called? Tom Hanks. Tom Hanks acts with Tim Allen. Tim Allen never acts with some girl, but Tom Hanks acts with her. Tim Allen is connected to her by order 2. 2 steps. 2 steps. Okay? So this is a connection. Now, the claim is you can virtually connect all the actors in Hollywood in no more than 5 connections, which is quite amazing. 6 connections. Okay, this is called the small world phenomena. Okay, and a good example would be I can actually connect Bruce Lee and Kevin Bacon. And you don't think Bruce Lee and Kevin Bacon actually would be in the same kind of movie, right? One guy is more like a action comedy. Well, actually, they're kind of similar, so maybe this is not a good example. But anyway, so Bruce Lee never acts with Kevin Bacon, but through this guy named Kenneth, I guess. There's a movie that connects Bruce Lee to this guy. So,   Bruce Lee has a number of 2 to Kevin Bacon. Now, the reason I call this Kevin Bacon number is because they don't just care who's connected to whom. They only care about Kevin Bacon, like the center of universe. Okay, so this is kind of a Hollywood fun games. The claim is nobody has higher Bacon number than 6. Okay, and this guy has Kevin Bacon number of 1, right? Because this actor actually appears in one movie with Kevin Bacon and doesn't. Okay, so now here's the deal. This is a network. Now this is called bipartite because it's not connected same kind of vertex. The vertex represent both movie and actors. So you have to contract this graph. So for example, this one is Jim something. This is Toy Story. This is Tim Allen. This is Toy Story. This is Tom Hanks. Okay. So this here has both movie and actors. Okay. Now, if you do some kind of computation as a pre-processing, so I make the connection between the actor and actor themselves, this one would be connected by number 1. Now, this Tom Hanks acts in this movie, and this movie, let's say, involve another actor, right? This Tim Allen would be connected to that actor or actress in 2 steps. So that's the connectivity number. Okay, Kevin Bacon number just count from Kevin Bacon, but let's do this for every pair, every single pair. Okay. By the way, this is what the data looks like. These are actually all the movies and all the actors together, and it's very big. Okay, this is a real database. And altogether, this database, again, this I did was I was giving a talk in 2018. So back then, we're talking about 144 actors, 1,177 movies. Okay, so movies here, actors over here is called bipartite graph. Never mind. But I want to make connection between actor and actor. So you can imagine that Tom Hanks, Toy Story, Tim Allen, right? Bruce Lee, some movie, some guy, some movie, Kevin Bacon. Okay. And I did this and I calculated eigenvector centrality to see who is really, in terms of co-starring, who is really driving Hollywood. And I was kind of expecting a very smooth graph. This is very surprising. I mean, this shape, okay, forget this line here. This shape I expect. So these are all the A-list celebrity, right? But there's one guy or one girl who stands up above the rest. This person. I'll let you guess who that is. Okay. So that's eigenvector centrality. And this is done through, this is using, now obviously this requires, because I was doing Python, it's a lot more complicated than just one line, okay? But it's the same concept. Another final example. This is good. This is one for you who are into logistics. This is actually all the Bangkok metropolitan center. So I live in Watthana. Watthana is somewhere here. I don't know what that is, right? So Bangkok has, I think, 30 or 40 districts. Okay, this line indicate adjacency. Okay, adjacency. So if you think of adjacency as some kind of distance, if I want to go from this thing, this district to that district, without visiting many other districts, I would choose the shortest path, right? Right. So in this case, the number that I'm interested in would be, okay, by the way, this is degree centrality. This is counting the number of neighbors. I think this is Bang Na or Yanawa. Oh, Chatuchak. Yeah, Chatuchak is connected to most, okay? But the one that I'm interested in is between the centrality. It means that if you're going to find shortest path in terms of minimum number of districts to traverse between any pair of districts, Chatuchak is still important. That's Chatuchak. But you know who came even more important than Chatuchak? is Dusit, which is just a little bit further up the road. Okay, and these are kind of like periphery. So this is something that's a very good project if you were to do something like logistic or supply chain, or a network of warehousing, that sort of thing, right? And of course, you can embellish this. This is only connection in terms of which district is next to which district, literally adjacency in that sense, right? But you can think of this warehouse is connected to that warehouse, and between the two warehouses, it has a big highway. So that's a big number. This warehouse is connected to that warehouse, but through a smaller street. So that's a smaller number. Okay. So your analysis may vary now because it's not 0 and 1 anymore, right? It could be 0, no street between two warehouses. It could be capacity, size of the traffic. Okay. Or conversely, congestion, in which case you want the thick line to represent the inverse of congestion. So if it's very congested, you want very thin line, so you don't want to go there, right? But if it's an empty road, let's make it a big line. So you can make weighted, okay? This is, I really strongly encourage you to think about this, because some of you, you think of Basai doing all this. Oh, by the way, this is the connectivity matrix. Okay, so basically this is the geographical data, right? This becomes encoded in terms of the district and connectivity. So basically this is a matrix of 0 and 1. Okay, I run through the algorithm. Okay, with Python it takes a lot of line, but Mathematica just one line, and then it would rank this like that. But it's not that many lines, by the way, with Python, because there's a library called Network X. Okay, Network X is a Python library dedicated for doing graph analytics or analytics on graph data. Okay, so if you want to do this in Python, it would take you probably 400, 500 lines. So I don't recommend you do that. I recommend you go to Network X, import it, and then it's still a little bit tedious, but it's not so much. And then this is the function. Okay, you just read the adjacency list, district name, related node, figure, and then you do the see, same word, eigenvector centrality. Okay, so because this one has been wrapped in an application, it's almost as easy to use as Mathematica, right? Just one line here. See, okay, eigenvector centrality of this. So you have to import from Network X. Network X is free, so you might as well do it. Again, you can do all this. Okay. By the way, this is actual data from the Bank of Thailand. This is secret data. The reason I could publish it is because I mask everything. So these are all the banks. These are all the banks. But instead of using the bank, I just randomly assign names, okay? And I use something like color palette or something. So there's a bank that's called fuchsia. There's a bank that's called sea blue or something like that. It's just random, okay? But the point is this: if you look at scan this. Yeah. If you look at the size of the bank, this bank is very important, the green one, okay? But if you look at the connectivity, the sixth one is very important. It's kind of like a big, but not the biggest, but it actually is the most important. So in any kind of crisis, if the Bank of Thailand is worried about injecting liquidity, I would recommend go to the fifth bank, not the 10th bank. The 10th bank looks like a big bank, but it's not that connected to other people. See? So I would recommend not looking at the green bar, but look at the blue bar. Okay. Likewise, if this were not network of banks, but network of friends, network, you see what I mean, right? Political influencer, fashion influencer. You guys are familiar with this concept, but think of the tools you have, right? You only have what? Think about it. you only have degree centrality, right? Who's a famous celebrity on Instagram? You look at number of followers, right? Right? But that follower is a เดี๋ยวโทรกลับไปนะจ๊ะจ้ะ If you look at the number of followers, that literally is the number of links. So that is degree centrality. Now, Instagram has more information than that. You would say this one is a popular influencer because she has 5,000 followers. This one has 2,000 followers. Okay? But when I am paying to advertise my product, I would pay Instagram to tell me who is more eigenvector central. It may be this one with only 2,000 followers. This one has 100,000 followers, but means nothing. You see what I mean? So that would be the equivalent of this one. I mean, I really want you to have this picture burned to the back of your head. This guy, right? Yeah. If you use a number of followers, if you look at the number of followers, okay, this guy is very important. 1, 2, 3, 4, 5, 6, 7, 8, 9. This one knows, maybe less, right? But this one certainly is more eigenvector central or something like that. Okay, so get the point. Get the point. So a lot of things are. That's why, and this has nothing to do with just this class, but you have to realize this is why platform business always wins. Because if you're a platform, you have the data to do all kind of analytics that's not available to you. Okay, so you know who's the important influencer. I, as Instagram, can do eigenvector centrality ranking internally. Don't give it to anybody, but you can pay me a lot of money and I can explain to you what eigenvector centrality algorithm is. And I say, I will push your product to network or Instagram influencer according to eigenvector or page rank centrality. Okay, if you were a company just looking at, oh, this one's a good celebrity, has 2,000 likes, this one has 50,000 likes. Maybe that 50,000 like doesn't really push your product. Okay, so this is that kind of power. So you always have more power if you have more data plus algorithm or analytics, right? Now, this here. Oops, where are we? Okay, so let's finally, I want to show you, and this is a little bit of hopefully we have time. Yeah, we have a bit of time. I was gonna talk a little bit of project, but I'll leave that to later. Okay, this is more important. Okay, so let's go to here. Now, hopefully this is not going to hang because this is it takes a while. Now, the last point is this. The last point is this. Even though, if you think about it, even though I draw it like this, right? The actual location here is not what's important, right? So I can actually put points anywhere I like. This is called embedding. Okay. What does it mean? Embedding means that I am going to embed, hence the word embedding. I'm going to embed the vertices in location space. By location space, I mean 2D coordinate. Okay, 2D coordinate. Now, I'm gonna quickly do this because hopefully your thing doesn't hang on me. Okay. This, okay, I download some data. Basically, this is United States. Okay. This is United States. You can kind of guess that this is kind of like Northeast or something. This is connected by location. Like, we were doing the district of Bangkok. Now it's the state of the United States, right? So there are 50 states in the United States. Okay. And this is basically connectedness. Now, it's a little bit tricky because with Alaska, it's connected to what? You can say Alaska is connected to Washington, and Hawaii is connected to California, but Hawaii is also connected to Oregon. Okay, so that's a little bit tricky. Never mind. So let's do this for Thailand. Okay. What we did, okay, was, well, first of all, I asked for ChatGPT to compile the list of connectivity, and I asked your friend Atamphon here to verify. This is basically it. Okay, this is all the Jangwat in Thailand. Thailand has 77, right? Right. So notice this kind of looks a little bit like Thailand, but it's kind of like not quite. You can think of it as, well, if I flip it, it looks like the country of Thailand, right? This is kind of like north. This is kind of northwest. This is northeast. This is southern part of Thailand. This is Prachuap, right? So this is Thailand. Now, because all I care is representing the line that connects the Jangwat together, the provinces together, right? And try to use that doesn't really matter location. I can do this. I can locate. So these are called all the different embedding. Okay. It doesn't matter. Think of it as those circles are connected by elastic line on a surface, a pool of water. You can move it around. So this is called embedding algorithm. Oh, I can do any kind of, some is nicer than the other. This is called grid, obviously. There's so the connectivity is the same. Okay, but the representation is not, right? Okay, so this is kind of like so this one make it look like a circle, all kind of stuff, right? But the one that we rely on tends to have the similar kind length of line. Okay, fine, no problem. Okay, so that's basically the adjacency. Okay, this is all the 77 Jangwat, right? And if you see an orange, it is 1. If you don't see orange, it is 0. And obviously it is symmetric, right? You can draw a line here, fold it. So this is a demonstration. Now, here's where I try to get a little bit, oh, yeah, forget, I'm going to come back to this, but let me just enter this. Now, what if I want to do both? Because Jangwat has geographical location, right? Why not do that? Why not, instead of arbitrarily put the circle of the vertices anywhere, let's put them on an actual latitude and longitude. That way I can show it on top of a real geographical map. Now, the step I did here is a little bit more involved, because what I did was I went to the database that has all the tambon. Tambon is like a sub-district. So instead of looking at the location of the district, province, I look at the district, the sub-province, the major sub-province, Ampere Mueang. Okay. So those are the guys, right? And now let's see what happened. Hopefully it doesn't. Yeah, it's running, it's taking a while, but you can imagine what I wanted to do. Okay. So I said that the location of the vertex doesn't mean anything, right? What matters is the connection. But because in this case, the connection is derived from geographical bordering, wouldn't it be nice if I display this graph so that the location is not arbitrary, like right now, just now, the circle, grid, and all kind of stuff. Let's make it actual physical location. So I can do that, which is what, ended up doing. And what I did, I'll show you, I'll send you in the line. It's actually what's called animation. So let me just skip to this because you might take a long time. So I don't know. Output. Okay. So it's going to look like this. So instead of embedding it in artificial dimension, let's embed it in geographical position. So it's going to look like this. Come on, just a picture. Come on. There, see? So think of this. So not only I know that these two Jangwat are neighbor, okay, but let's do that, right? Let's do that. So you can imagine that even though in graph analytics, the location of the nodes don't matter because you only care about connection, okay? You can, if the location of the node has geographical interpretation, why not? Why not? Okay. Now, here's the next step. What if, and this is the last thing you need to learn as a knowledge for exam, but I don't think you can do it. You guys remember TSNE? Bunch of data point exist in high dimension. Put them in 2 dimension in such a way that if you are close in high dimension, you are also close in 2 dimension. Okay? Now, imagine instead of if you're close in high dimension, you are close in low dimension. How about if you are closely connected in the network? By closely connected means how many steps do you need? That's interesting, right? It's interesting. So imagine that each share is a step. So you two are actually very close to each other because you only need 1 share step, right? This girl and you are quite far apart because you need many share steps. 1, 2, and 3. Okay, occupy share. Okay. Likewise, hey, wait a minute. So instead of positional closeness and line you in front of the class relative to the position like T, S, and E, how about you two are close if you can get to each other within 1 step? That's like as close as you can get. If you need 2 steps to get to each other, you're not so close. Let's use that as distance metric. So you start with the network, then you throw away the network, right? You throw away the network and use the closeness. What if I embed you like that? That is called generalized graph embedding. Okay, so let me say it again. I can embed location of the nodes according to any kind of option I think looks pretty. A square grid looks pretty, a circle looks pretty, or sort of like evenly spread out looks pretty, or sprinkly or circular looks pretty. That's my choice. Okay, but that at the end of the day, that's how I locate the vertices. Okay, so that's embedding, but I use an algorithm that makes it look pretty. Okay, I can embed it not in the way that looks pretty, but in a way that looks like real life, because this happened to represent real life. Finally, I can located in a way that's similar to, what we did in dimensionally reduction, which is that you should be together if you are close together. Except closeness in this sense is not geographical closeness, but network closeness. And network closeness in this case is defined in terms of how many steps do I need to get to you. Okay? So with that in mind, now that is called graph embedding. You were asking earlier about neural network. This is where the advanced neural network research is being done. There are many recipes. In fact, because there's so many recipes, if you're going to do serious graph neural network, you need to go to Python. Why? Because as new algorithm comes out, they publish in Python. Okay. So based on this, okay. Now, so you saw earlier, right? Where are we? Okay. So you saw that I can choose any kind of embedding, yeah, to make it look nice, right? So I happen to think that this thing looks nice like this or whatever. I can just change it. Okay. Oh, it's running. It's just taking for. Oh, sorry. I actually run animation at the end. I shouldn't have done that. So it's going to take a while. Now, this is what's called Node2Vec. This is actually a Python algorithm that I run separately. Once I run separately, it gives a location so that Jangwat are close together based on how many interstate crossing do you need? Inter-province, sorry. Okay? And you know what that looks like? It looks like this. I have to pause the calculation here. I'll just go to the example. It looks like this. This is Narathiwat. These are all the 77 provinces, but the way it's curled up, it's not meant to look pretty. Like I tried earlier, right? Square, circle, that looks nice. No, this has not, it doesn't have that kind of embedding criteria. It doesn't represent geographical location, but it represents closeness. So provinces that are close together, now I should make this bigger so you can see, are those that you can travel to and from, crossing least number of border. Okay, so that's what it looks like. Now the reason this thing is hanging because just for fun, and this you can do this with Mathematica. I do what's called animation. So I did a GIF. Where's the GIF file? So I start from geographical location and I move it to whatever. Okay. It's kind of morphing. Okay. But this one is not that interesting. The one that morphed from geographical to that neural network learn is more interesting. That's this one. Graph embedding in there. Yeah, this is the coolest one. Okay. Start with actual geographical and sort of like move it, morph it so that oh, is this yeah, I was showing you the wrong one. It's this one. So it's even now. Let me ask you this question. Now, put your thinking cap. What does this do? It creates a representation of different province by two numbers, the X and the Y location, such that province that have closeness in network space can be close together. Now, I happen to define the closeness in terms of cross-border, right? What if I didn't do this? What if I did this by, say, political alliance between politicians across Jangwat? I can do this, and I can see which Jangwat are politically partners or something like that. You see what I mean? Does that make sense? Okay. Now, so in this case, you know, provinces that are close together are provinces that happen to be geographically close, but it could be politically close. It could be demographically close, right? Imagine I did this in country, right? And instead of having cross-border, I say something like, two countries are connected by the number of international cooperation forum they belong to. So United States and UK would have many lines. They have NATO, they have something else, they have God knows what, right? Thailand and United States, we also have one line. Okay, I think Asian Pac or something, Asia Pacific, right? And a few other. Within Asian, we also have country lines, right? Thailand and all the, Indonesia, Philippines, Malaysia, all the ASEAN countries are connected, right? What if I use connectivity matrix of countries? Okay, and instead of locating A to make it look nice, like a circle, rectangular, just make it look pretty, or B, location on physical geometry, geography, latitude and longitude of a country, I do this. I can actually see, hey, in terms of political international alliance, who is Thailand really close with? Right? Now let's do this again. I don't care about political alliance. I care about how similar our demographic vector is. So let's say we have a demographic factor with age, sex, education, median income, and all this. You can say countries are close together or far together, depends on the distance. It's a bit tricky because, you know, the dimension is not normalized, but let's say you can, right? So thinly populated countries with high GDP per capita are close together, right? High GDP per capita, but very densely populated, a little bit further out. Two densely populated, low-income country will be very close together, right? So in any dimension you want, in any dimension, as long as you have the distance. So now, wait a minute, I don't even need the graph. That is a generalized embedding problem. Okay, so that gets back to the T-SNE kind of thing, right? So you can see that graph and non-graph data, yeah, I treat that separately. Okay, chapter 1 to chapter 6 get you to tabular data basically, but chapter 7 is graph data. But in reality, whether or not you look at things as from a graph perspective, sometimes there are many ways of looking at things. So country definitely is very, very, very similar, right? So if I look at country on a demographic, socio-economic data, it's a tabular data. But if I take the similarity measure between those demographic, socio-economic attributes of different countries, now the closeness becomes a property of two entities, two countries. So from tabular data, I create graph data, right? So it's not that it's AI. It's a distinct discipline, graph data and tabular data. But you can see that, you know, once you know well enough of both these things, you can start to see how you can jump around. And these are kind of like data analytics gymnastics that is necessarily when you're a professional data scientist. Okay. So if your career is data scientist, you will be ending up coding or programming particular technique. You wouldn't do this kind of thing. This kind of, hey, wait a minute, let's take different entities and find out how close they are, turn that closeness into adjacency matrix and do some kind of embedding. This kind of thing is where principal data scientists start to imagine how you would do the analysis. Okay, but when you start to create, you just have to be good at programming and coding different techniques and testing and so forth. Okay, this gets you more like 2 weeks back when we were working with building the machine learning, right? Supervised machine learning and finding the error, unsupervised learning, find machine error, find confusion table and all that. And okay, so that's it. That's called the content. So I would encourage you. Now, I have obviously done a lot of analytics that's not in the notebook. For example, this one here is done separately. I have done many things on separate. What I'm going to do before I get to the final version of the textbook is find out which one is kind of like more, maybe I'll stick this in the textbook as well. But what you got with you right now in the notebook, in the textbook, is pretty much what I decide to be the final organization. Okay, so once again, chapter 1, what does it mean to do data analytics? What's data? So basic introductory concept. Chapter 2, how to work with Mathematica, because we're going to be using that. That's a very high level thing. It's very easy. Okay, right? Chapter 3, hey, let's analyze data using interactive visualization. So you have to know how to do this different plot, different things, and portray, radial basis plot, radial axis plot, all kind of stuff. Make it interactive with manipulate, which you will test it on the exam, right? And then chapter 4, let's go old school. Let's go classical probability statistics, but do this with Mathematica, with real data. You see that it's very easy. Much easier than traditional statistical software like eView or Statistica, I think. And then chapter 5 and 6 is about machine learning. Not all machine learning, just the part of machine learning that's very good for building data analytics. Chapter 5 being unsupervised, chapter 6 being supervised, right? But like I said, maybe you can use one as part of a pre-processing for another, or one to show the result of the other. So in an actual application, there'll be a mix. Most of my past project is also a mix. It's never purely unsupervised learning or purely supervised learning or purely visualization. It's usually a mix of all three. Okay, and finally, chapter 7, you try to do all this, but not on tabular data, on data that pertains to graph. There's an inherent structure where information does not pertain to one entity, but a pair of entities. Okay, and then you can do unsupervised. You can do things that doesn't have machine learning. You can do things that have to do with unsupervised machine learning. Finally, you can do things with supervised machine learning on graph. It's not covered in this class. One of the reasons is because it's also a very new area, but you can imagine what kind of prediction can you do? And this is the last example I would give. Now, with friend network on Facebook, it's deterministic. You know who's friend with whom. Imagine that I am FBI and I want to know network of criminals. I happen to know for sure that this criminal and that criminal are connected. However, there's something that's dangerous about this guy and that guy being connected, but I don't know if they're connected. So this information is not revealed. What can I do? This is where prediction comes in. So you can train your model based on, if this is a network and I train it and I give it true data that I don't say is connected yet, and I ask, what's the probability that it's connected? So instead of getting X and predict Y as a probability of rain, I get network connection, adjacency matrix, I train on it, and I predict whether or not I and J in fact are connected. So even though you have never taken a photograph of these two criminals together, you can predict, hey, this gang and that gang is actually connected. Okay, so become prediction. It's called link prediction. That the word link stands for edge, basically edge prediction. Okay, but the application name for that is called link prediction, predicting whether or not the link exists. Now, how else would you use it? You know who else use it? Facebook. Why do you think they have this friend suggestion? Because you are not connected, but the graph neural network model tells you you should be connected. And if you are connected, you're probably going to generate a lot of contents and, I don't know, gossip or whatever. Okay, so right now you are not friend, but based on who you're connected, based on who these are connected. Now, actually, link prediction in Facebook has been done a long time ago without this technology. They use something more primitive, like common set of denominator, right? But a very advanced Facebook algorithm is based on something like this, called link prediction. And I predict that this guy and this guy, which are not connected, should be connected. Okay. So like I said, the 5 years ago, Facebook probably would have looked at who this guy know, and the common denominator, right? That's sort of like intersection of friends. But now they probably use something more advanced like link prediction. And link prediction would be using graph neural network. So get used to that word. Finally, and this is the final word for the day. Graph neural network is generalized into a concept called geographic deep learning. What did I say? Geometric deep learning. Graph deep learning. I'm really weird now. Okay, something's wrong with my brain, but it's one of those things, GDL. Okay. Geographical deep learning, graphical deep learning, geometric deep learning. I think it's geometric deep learning. Anyway, it's the future. It's the future. So now the hot area of machine learning / AI, the two area, very hot. Large language model and this geometric thing, which might as well call it graph learning. Okay, graph learning, graph embedding, this is huge. Large language model, you already saw that, ChatGPT and all that kind of stuff, that's huge. These are the two huge things going forward. Now, I personally am a lot, obviously, you know, given my past work with eigenvector centrality, I tend to like to play in this space, but I'm not going to ignore large language model because that's going to be very important. Okay, so that's it. Yeah, that's it for today as well. So here's the deal. Here's the deal. I might do a little bit. I don't know how lazy you are or how not lazy I am. If you're lazy and I'm not lazy, I might do some kind of topic list that you should be responsible for. But essentially, if you look at the notebook that I just sent you, right, just go through that. Just run step by step. All you have to do is shift enter, guys, and just follow through. How hard can that be, right? And just read it. Okay, it's already well organized along that sense. There are other use case, advanced technique that I haven't squeezed into, but you don't have to worry about that. Okay, so next week, come with prepare, not quite a pitch, but sort of like, imagine I have 10,000 baht to give to the team, each team, to go buy something, buy data, buy whatever, okay? And you have to say, okay, I want to study this problem, it's worthwhile, give me money. So it's a pitch, but not pitch for the product, okay? Pitch for the problem. So prepare that. You can do it any way you like with notebook, okay? Or you know, don't be that fancy. I'm not all that keen on this fancy, hackathon pitch. Have you ever wondered what it's like to be this and no? Just go right to the meat of the content, okay? And then you work, and this is important, and I can't emphasize this enough, but you guys always fail. When your friend present, pay attention. Help your friend. Criticize your friend. ask your friend about assumption, ask your friend about data, grill your friend, friendly manners, don't get into fist fight or anything. Okay. But be critical about your friend's presentation. Don't just say, oh, when's it going to be my turn? Okay. I really want you to do that. Please. I ask this every year, and every time somebody presents, and you just go look at your own presentation. Forget your presentation. Look at your friends. That's what I want for next week. Okay, and Pi Kong Kam will be with you. Okay, good. I'll see. Yeah, I'm running out of time. I'll see you guys next week in Zoom or here or whatever.